Hello students, today I am going to cover the syllabus on BSc 5th semester, paper 1, real analysis, which is the syllabus of Karnataka University, in which unit 1, Riemann integration. I am Dr. Krishna P. Chowreddy, Government First Aid College, Naragon. So in this session, I would like to give a necessary and sufficient conditions for R integrability and properties of R integrable. So now let us see that this property, Darboux property, which will be helpful in deriving the necessary and sufficient conditions for R integrability. So what it says that this Darboux theorem, suppose the function is bounded in the closed interval, then for every epsilon greater than 0, there exists a corresponding delta greater than 0, such that for every partition, in any way you can have a partition there. So UP of is less than always something added with the upper integral, and LPF, it is lower sum, it is greater than something removed from the lower integral. That lower sum is this relation. So now let us see that necessary and sufficient conditions for R integrability. So statement of this condition is a bounded function f of x defined on a closed interval AB, if and only for each epsilon greater than 0, there exists a partition P of AB such that UPF minus LPF is less than epsilon. So we have to prove one is necessary conditions, another one is sufficient condition. So in necessary conditions, we start with the supposition f is R integrable. Suppose that f is R integrable, then we have that is lower integral equal to upper integral that equal to integral. And also we know that the definition of the lower integral as well as upper integral. Lower integral is supremum of the lower sum and upper integral is the infimum of the upper sum. So now let us see that by using the Darboux theorem, let's assume that let epsilon greater than 0 be given. Then there exists a delta greater than 0 such that each partition P of AB with norm P, maximum length of that partition is less than delta. We have that upper sum is less than by using Darboux theorem, so that we can write it upper sum is less than upper integral plus something epsilon by 2. So just I can rewrite this upper integral equal to lower integral that equal to integral. So make use of that property, that concept, so that we can write it, it is integral plus epsilon by 2. And similarly, LPF, that is lower sum is greater than lower integral, something removed from this lower integral, that is the used in the Darboux theorem. So it is also that is lower integral equal to integral minus epsilon by 2. Just I can rewrite by taking a minus throughout on both sides, so that we get this relations 1 and 2. That adding these two equations, we get a conditions UPF minus LPF for each partition P with maximum non P is less than or equal to delta. So also we shall see that conversely that condition is sufficient condition. Conversely, suppose this condition holds, means what UPF minus LPF less than epsilon, then for any partition P, we have the property there. So as we know that property we have derived in the previous sessions, so that LPF is always less than equal to lower integral, that should be less than equal to the upper integral, that should be less than equal to the upper sum. So just making use of that is this upper integral minus lower integral, that is should be less than equal to the upper integral minus lower integral, that should be less than epsilon. So then let epsilon already be arbitrary, it is very small, however it is small, which close to 0 there. So if I take a 0 there, then it is lower integral equal to the upper integral, then ultimately obviously f is R integral. Hence f is R integrable or integrable in AB. This is the proof of necessary and sufficient conditions for R integral. So now let us see the examples based on that conditions for R integrability. So by taking function is x square here over the interval 0, 1, is this function is R integrable? Definitely it is R integrable. When we proved before that the integral already f of x equal to x square, which is exists there, because it has its own derivative, it has its if you take a ordinary integration there, so definitely it is x cubed by 3 there. So definitely it is 1 by 3 answer we'll get at the end. So that is what we have. But with the help of condition, we need to prove this result. It is R integrable. So that if so, find the value of R integrable also there. Do the same for the interval -1 to 1. Yes. So now we shall see that this condition, it is true for every partition P with small enough norm using Riemann's necessary and sufficient condition. It is enough to find one partition such that equation 1 holds. Means what? That condition 1 holds. UPF minus LPF O1 holds means satisfied. Therefore, take the partition P, that is P is J by N for all J is running from 0 to N for the interval 0, 1. On every subinterval, J minus 1 by N to J by N. Then the maximum of F occurs on the right hand side and minimum of F on the left hand side. Therefore, condition of UPF minus LPF, that should be, you can have a, that is, this is here. You can, it is upper sum, and this what you can have to find through the examples there, through the function there. So then it is a summation of delta R relation, that is 1 by N. So then ultimately this is what we can have a length between the this is a that is J by N whole square minus J minus 1 by N whole square. That is definitely, it is depends on the function we have there. So that is what we have. This is got it from, that is the summation of delta. So that is it, ultimately it becomes 1 by N cube. So because it is here 1 N and N square here. So that ultimately what we get it here. So what is the end of this result? UPF minus LPF should be wind up with the N plus 1 by N square. And but since the last expression which converges to 0, when it is 0 as N approaches to infinity, as N approaches to infinity, it means what? As long as you can divide as many divisions you have there, definitely you can, that converges, that expression converges to 0. So that is what the Riemann's theorem shows, that the function f of x is x square is indeed integrable over the interval 0, 1. So the Riemann's necessary and sufficient condition has indeed simplified our computation, because we are now able to pick one partition that is the best suited for our particular function or any interval. So now let us see the properties of R integral. So theorem 1. So every continuous function is R integrable, or every continuous function in the closed interval is also R integrable in the closed interval. So or else you can state like this: if x is continuous in the closed interval AB, then it is R integrable over closed interval AB. So now let us see the proof of this property. Start with the, we assume that function is continuous in the closed interval, then it is obviously bounded in that closed interval. So now let us divide that interval. Let B be a division or partition of AB, such that in each of the subintervals we have, that is the relation is UPF minus LPF. That definitions you can substitute here in the UPF upper sum minus lower sum, and ultimately delta R is common between them, so that this MR minus MR is less than epsilon. That ultimately it is what we have a relation ultimately always supremum over the subinterval and minus infimum over the subinterval. This relation is always less than epsilon, and also summation of delta R is also B minus A. So ultimately we got it at the end UPF minus LPF by making it as some simplifications by taking anyway that epsilon is epsilon prime by B minus A. So ultimately we got it, that is the, at the end this function is, this condition has satisfied, so the function is R integrable in AB. Hence every continuous function is R integrable in the closed interval AB. Now let us move to the next theorem. Every bounded monotonic in the closed interval AB is also R integrable in the AB. Here also we can have that, see that let fx is bounded and a monotonic increasing one part. As you know that monotonic function, that so either monotonically increasing or decreasing, that definitely it is monotonic. So that now let us see that fx is bounded and monotonic increasing closed interval AB, and also let D be a division or partition of AB such that in each of the subinterval relation delta R is relation E is always that length of that subinterval is less than always epsilon. Since fx is monotonic increasing in each of the subintervals xr minus 1 comma xr, we have that supremum and infimum based on the function that is f of xr and f of xr minus 1. Now let us take that is the start with that is up of minus lp of definition, so that also we have that capital MR is f of xr and small mr is f of xr minus 1 with the delta. Delta R is less than epsilon, that is what we have. Just by expanding this summation, wind up with that is the f of xn minus f of x naught, that is f of b minus f of a. So that is what we have, that this condition. And also let it be epsilon is epsilon prime by f of b minus f of a, then ultimately that equation 1 becomes, it is the condition as satisfied. So obviously this function is also R integrable in the closed interval AB. Similarly, if fx is bounded and monotonic decreasing function in the closed interval AB is also R integrable in the closed interval AB. Hence every bounded and monotonic function is also R integrable in AB. Now let us move on to next theorem. Every bounded function which is discontinuous at finite number of points in closed interval AB is also R integrable in the closed interval AB. Now let us take some points, that points which are the those points with the function at which that is discontinuous, but it is bounded. So let us see that let x equal to c1 to ck. Ck be the points at which the function is discontinuous, but it is bounded in that closed overall closed interval AB. Let D be a division of a partition of AB such that in kth of the intervals there is a point of discontinuity, but remaining n minus kth intervals, so the function is continuous. So that only we need to see that at which that whatever we assume that let x equal to c1 to ck, at which that function is discontinuous, but remaining that is n minus k at which the function is continuous. So that let us see that the division is such that in each of the subinterval supremum minus infimum less than epsilon n minus k, it is in the subinterval. So just taking that is up of minus lp. So that definition we have clubbed with here. So 1 to n minus k, and this is k2, that is what we have there. So this is ultimately I want to make it as a 0 there. So what I do there, and this I want to make it as less than epsilon. If capital M and small m are the bounds of f of x in the closed interval AB, then always that is mi should be less than m and small mi should be greater than m. So that ultimately mi minus m small mi should be less than capital M minus small m. So and also summation of delta R over 1 to n, it is also that same. So that ultimately what we have there, so we need to prove this condition there. So what is the condition there? up of minus lp of, that is this, and this becomes this summation of delta, this is the k minus, so what is the m minus capital M k delta, that is what we have there. Ultimately this term goes to 0, this condition has satisfied. So hence this function is also R integrable. So now let us last property in this section, that is if fx is bounded and integrable in the closed interval AB, and capital M and small m are the bounds of f of x in the closed interval AB, then we have that is integral lies between this relation. Now let us start with the proof of this here. D be a division of AB, same exactly as we have seen in the previous theorem. So that let m and m be the small m be the bounds of f of x in the closed interval B. Then for every value of r, we have that is the relation. Always in the subinterval we have a that relation we have. Just plugged into that all that m and delta, so that this m and this capital M are the independent of those summation, lastly wind up with this relation. And also since fx is bounded and integrable in the closed interval AB, then also we have this relation. So from these two relations, so we can write it the what we require, the relation at the end. So another relation there, another theorem, if fx is bounded and integrable in the closed interval AB, then k into f of x is also bounded and integrable in the closed interval AB, where k is positive real number, and relation, that is integration of the constant into function, is always, that is k into integration of the function. So that is, since here also, that is, we can make use of the definition of boundedness. Since fx is bounded, then there exists a number k belongs to R. Ultimately, this is that f of x, modulus of f of x should be less than or equal to k for all x belongs to closed interval AB, and you can k multiplied both sides and k inside the modulus. Ultimately, k into f of x is also bounded in the closed interval. And also, let us same assumption starts with, as we have started in the previous theorems, so that let B be a division of AB and the capital MR be the bounds of f of x in the subinterval xr minus 1. Then for every value of R, we have the upper integral and lower integral definition. From make use of those definitions, since fx is integrable in the closed interval AB, then we have, that is, upper integral equal to lower integral and that equal to integral. So now let us see that proof of this. So now I want to prove that here for k is positive, so that k into mr, k into small mr be the bounds of k into fx in the subinterval. Then we have that upper integral, that definition, that is infimum of UPF, that already you have there. Ultimately, this upper integral equal to integral, and also lower integral similarly. Then ultimately, this relation 4 and 5, we get it, that is the integration, upper integral equal to lower integral, that equal to integral there. So that integration of k into f of x equal to k into integral of f of x dx. So this is the reference we have used in this session. Thank you.